Alright, hello everybody. This will be my short video covering NAS, or nucleophilic aromatic substitution. And so in this video, I'm just going to go over kind of the mechanism, what's needed for a nucleophilic aromatic substitution, and what kind of product you can obtain through this reaction. And so we'll start Okay, so nucleophilic aromatic substitution is essentially kind of the reverse of EAS, which you learned. And so what's required for NAS is one, kind of an electron poor aromatic system. So something with an electron withdrawing group, something like nitrobenzene or something like that, okay? And secondly, you need a good leaving group, okay? Group. And thirdly, you need a nucleophile. And so for NAS to work, you need these three things. You need an electron poor aromatic ring with some kind of electron withdrawing group on it, a good leaving group on the ring, and then a nucleophile to displace, okay? And so generally, the reaction goes as this. So you have your aromatic system with a electron withdrawing group. Let's just use NO2 because that's a very common electron withdrawing group. And a leaving group. Let's just use chlorine or chloride here, okay? So if you treat this aromatic system with a nucleophile, let's just use cyanide in here, okay? Cyanide is nucleophilic, and you'll get displacement of the chlorine, leaving you with your nucleophile where the chlorine was, okay? And so that's important because in EAS, the different substituents you have around the ring kind of dictate where your added substituent is going to go, right? So if you had an electron donating group, your substituent would go ortho-para. If you had an electron withdrawing group, your substituent would go meta. Here, that's not the case. With NAS, your substituent goes where your leaving group is, okay? So it doesn't matter where that chlorine is. It's para to the nitro group, and so the cyanide will go para as well. And so the mechanism for this is as follows. Oops, Cl. So your nucleophile, your CN, right, tacks at the same position as your leaving group, okay? This creates a negative charge. You can think about it as a negative charge, or you can think about it resonating, right? Like this. And then this can kick back down, right? And kick out the best leaving group. So cyanide is not a great leaving group. Chlorine's a much better leaving group. And so the chlorine will leave instead, which will give you your product. And it's drawn there. Like that, okay? And so that's essentially how all NAS reactions go. Now there's some key things to take into account here, right? So remember how I said that the positioning or the position of your electron withdrawing group doesn't matter in directing where your nucleophile goes. The leaving group is where your nucleophile will go. However, there are different effects of where your leaving group is in proportion to your electron withdrawing group that will affect the rate, okay? So take this for example. So we have this para-chloro aromatic system versus the meta, okay, compared to the nitro. Okay, so if you do NAS with both of these, with, say cyanide again, you'll get the cyanide at the position of the leaving group. But the rate of which the reaction proceeds is a lot greater for the para-nitro versus the meta-nitro. And the reason for that is because the para-nitro has a lot more resonance structures when the cyanide attacks in compared to the meta, right? So if you look at the resonance structures, so if we have this complex again where we just do para, right? Let's see now, the CN attacks in here. Right, you have this resonance structure. You have this resonance structure. You have this resonance structure where you can resonate up into the nitro group. And finally, you have this resonance structure, right? So you have all of those resonance structures. For the meta, I see those 5. For the meta, right, to see an attacks, right, you can only have this one, right, this can only go here, to give you this one. Right, and then the last one would be here. So you miss out on this important resonance structure right here, okay? You don't get that one with the meta, and therefore the meta proceeds a lot slower. It's also, and that's why this para positioning gives a faster rate of reaction compared to the meta. You can also do the same example with ortho as well, and see how many resonance structures you can draw. One more thing I wanted to mention is the more electron withdrawing groups you have on your ring, the faster the reaction will go. So we have right, so the rate of the tri-nitro aromatic system is going to be greater than the di, which is going to be greater than the single one, right? Well, because of this resonance stabilization of the negative charge you make when you add a nucleophile in. So key takeaways here: know the mechanism, know that the positioning of the leaving group impacts where the nucleophile will go, but the position of the electron withdrawal group doesn't, right? And so the position of the electron withdrawal group will affect the rate of the reaction, but not where the nucleophile will go. That's the important thing to know. And also that the more electron withdrawal groups you have on your ring, the faster the reaction will go. Okay, and so it's the position. So the key thing is the positioning of the nucleophile only depends on where the leaving group is, not where the electron withdrawing group is. That only affects the rate of the reaction. Okay, that's all. Thank you.